Hello mathematicians, we're now going to revisit completing the square, particularly in terms of how it relates to the graph. The advantage of completing the square is that it gives us a way of determining the vertex, the turning point of our parabola, and of finding the zeros if they exist. The way that this is possible is that when we complete the square, we get an equation for the parabola in this form, that y equals a outside of x minus h squared plus k. And you might remember that if we change the value next to the x, and if we add a constant, what we do is actually translate the parabola. We move the parabola. So if we had the parabola y equals ax squared, for example, we know that that's a parabola like this. We also know that putting a minus in there shifts the parabola to the right by h places, so it shifts across h, and we know that adding k to it shifts that point up k. So the vertex has gone from being 0, 0 to being the point hk. If we then put y equals 0 into this form of the parabola, or any other form, we can find the zeros, if they actually exist. So remember, the zeros are the values of x at which y equals 0. So they're the values of x at which we cut the axis. So let's have a look at this process in action. So it's important to remember that we've got two things. We're using the skill of completing the square, but we're aiming to get our equation in this form. So we've got y equals x squared minus 4x minus 5. So if we just start with this part, forget about the minus 5 for the moment, or shift it over here if you like. What have we got to do to complete the square here? Well, we have to take half the coefficient of this, which is -2, and then square that, and it'll always be positive, so that's plus 4. So what I've now done is that I've added 4 to the expression. So if I've added 4 to the expression, I then have to counteract that by taking 4 away. So that overall I haven't changed the expression. But what I have done is that I've enabled myself to write it as a perfect square, x minus 2 all squared, and I have another 9 subtracted from that. And what that tells me is that the vertex has gone from, or the vertex of this parabola, is no longer 0, 0, but it's actually 2 minus 9. So my parabola has its vertex across 2, down 9, so it goes something like that. Plus 2 minus 9. I should have been a little bit more careful about where it cuts the y-axis, but we can see it cuts the y-axis at -5. Where does it cut the x-axis? Well, I could have just gone back and factorised this, as I always could do, or I can put y equals 0. Now, if I put y equals 0, that gives me 0 equals x minus 2 squared, all squared, minus 9. If I shift that 9 across the other side, that gives me 9 equals x minus 2 all squared. If I take the square root of both sides, I get plus or minus 3 here, and x minus 2 here. So finally, I get two possible values of x. If I take this 2 over to the other side and add it to minus 3, so plus 2 minus 3 is minus 1, and plus 2 plus 3 is 5. So that's the value of these two zeros here. X equals minus 1 and x equals plus 5. Now with my next example here, y equals x squared plus x plus 1, again, x squared plus x, and I'll shift the 1 over to here. What do I need to complete the square? I need half of 1, and then I need to square that, which will give me a quarter, so I need to subtract a quarter from there so that I haven't changed the equation. So that gives us that y equals x plus a half all squared. plus 3/4. Now that tells me that my parabola has its vertex shifted left to minus a half and up 3/4. So this point here, the vertex, is minus a half and 3/4. Parabola is concave up, so it goes like that. So there are no zeros. I can tell from sketching the parabola. But if for some reason I didn't pick that up, if I then tried to solve my equation here by setting y equal to 0, then I would have x plus a half all squared. And if y is 0, if I take that 3/4 over to the other side, that would be minus 3/4. And of course I then can't take the square root of a negative number. So there are no solutions to that equation. That would be the same as if I tried the quadratic formula up here, and I would find that I had the discriminant, or the bit under the square root sign, being negative. Because you might remember that we said way back when that completing the square is actually the basis of the quadratic formula. Now, what if my quadratic expression is not monic? Well, I just work on this part here and take out the common factor, whether it gives me nice numbers or not. So I've got 2 outside of x squared minus 6x, and over here I'll shuffle my 16 away. What do I have to do here? Half of that is negative 3, square it, that's 9. And I've added, this is where it gets a little tricky, I've added 18, that 2 by 9, so I have to subtract 18. So I've got 2 lots then of x minus 3 all squared minus 2. So what's that done to my parabola? Well, this 2 has just affected the steepness of it. We know it's closed it up. The vertex is now at 3 minus 2, so we come out 3 and go down 2. It's concave up, so my parabola looks like this. It cuts the y-axis way up here at 16, and it cuts the x-axis here and here, which we find, as we did before, by putting y equal to 0. So when 0 equals this, then I just solve this. So if I take that 2 over to the other side, then divide by this 2, that will give me that 1 equals x minus 3 all squared. Square root of both sides, plus or minus 1 equals x minus 3. So therefore x is going to equal 3 plus minus 1, which is 2, or 3 plus 1, which is 4, which fits with our sketch here. And lastly, what happens if it's, well, monic or not, doesn't matter, but it's got a negative? Well, I like to take the negative outside this bit again to make it easier. So I've got minus outside of x squared minus 8x. Shuffle the 15 over here, it's still negative 15. What have I got to do to complete this? I want minus 4 all squared. I've now added minus 16, so again be careful, which means I have to add plus 16 to cancel it out. So I've got minus outside of x minus 4 all squared plus 1. What has this done? It's given me a parabola which has its vertex at 4 and minus 1. So across 4 down here at minus 1. And it's concave down. So I can tell straight away there are no zeros. So there's no point going through the process of putting y equals 0. Now our last question, last example, is one which just makes you stick strictly to what you know without trying to invent some new maths. So explain why any quadratic which has a vertex of 0, 1 has this sort of equation. So if we think of this equation and we compare that with our general equation that we saw up above, which is that if we shift the vertex, or if we write the parabola in the form a outside of x minus h squared plus k, that was when we shifted the vertex from 0, 0 to hk. So what have we done here? How do we make this look like that? Well, we just say that this is a outside of x minus 0 all squared plus 1. So we can read off then the coordinates of the vertex are 0 and 1, which is exactly what we needed up here. So how would I set all that out as a more formal proof? I'd say something like this. Since y equals that, then y equals ax squared plus 1 equals this, hence vertex is 0, 1. And that's irrespective of the value for a. Now I'll just do one of these, well, I'll do part A then. So what this says is that there's a family of parabolas all passing through 0, 1 as the vertex. And what the parabola looks like, or what its exact equation is, depends on the value of a. So if we know that the particular parabola we want passes through 1, 3, again, we use the fact that you already know that if it passes through 1, 3, then 1, 3 must satisfy our equation. So it must satisfy y equals ax squared plus 1. We don't need to write the 0 in here. So if it satisfies it, that is the left-hand side, which is y, is 3, equals a times x squared, which is 1 squared, which is 1, plus 1. And now we just solve that. So that means that a times 1 squared, which is just a, equals 3 minus 1, which is 2. So a equals 2. Therefore, the equation of the quadratic, or the parabola, passing through 1, 3, is going to be y equals 2 x squared plus 1. Now the rest should work exactly the same. So have a go at 8b.